A rather common student error on exams is to use just any equation that seems to fit the given data, without taking into account, for example, for what point in space and time the given data are true. I had a student once that said that the exam I gave was like equation bingo. But although it is true that you might get lucky when choosing an equation to use based solely on the information given in the task, you need to understand equations in order to be sure what information you need and that your solution is correct. As an example, to calculate an amount from concentration and volume, you can multiply the concentration with the volume, but only if the concentration is the average concentration of that specific volume. You can't just look at the units, multiply mole per liter with liter and be sure to get anything valuable. Understanding what the equations tell you is especially important when you deal with equations based on the assumption of chemical equilibrium. To achieve chemical equilibrium, you must have a truly reversible reaction. If the system is far away from equilibrium, the net reaction rate is large. For example, if the concentrations on the left side of the reactions are too large compared to the equilibrium state, the net reaction rate is large, and towards the right side, rapidly decreasing the concentrations on the left side and rapidly increasing the concentrations on the right side. As the system approaches equilibrium, the net reaction rate diminishes. If we are theoretically strict about our reasoning, we can draw two conclusions from this. 1. It takes an infinite time to reach equilibrium. 2. It is impossible to reach equilibrium in a flow system, since the inflow of new material continuously disturbs the system. As engineers, however, we are often satisfied with simplifications that give us small enough errors. Thus, we may, under some circumstances, modify our conclusions and say that we might assume equilibrium when the residence time is long enough. Advanced students should note that there is a difference between a closed system and an open system. In a closed system, for example a batch reactor, we get closer and closer to the chemical equilibrium the longer we wait. In an open system, that is, a system with a flow through it, we get closer and closer to the steady state the longer we wait. The longer the residence time is in our flow system, the closer this steady state will be to the chemical equilibrium, but the chemical equilibrium state can never be reached. Despite this, I myself assumed chemical equilibrium in a flow system during my PhD studies. I was modeling soil chemistry, and the flow of water through the soil is on average so slow that you safely can assume that, for example, the autoprotolysis of water and the carbonate reactions are at equilibrium and still get accurate results. In a heterogeneous system, for example with a solid adsorbent and a liquid containing some adsorbate, we may thus be able to assume equilibrium in batch systems, and calculations assuming equilibrium in flow system may provide valuable information. In a batch system, we are close enough to chemical equilibrium after some time has passed. Thus, although the initial concentration Q on the adsorbent is not in equilibrium with the initial concentration C in the liquid, before they have been in contact with each other, we can reach equilibrium between Q and C in the reactor if we wait long enough. Thus, when we empty the batch reactor, Q and C may be in equilibrium with each other. Note that Q and C must represent concentrations at the same point in time. In a continuous flow system, Q and C can only be in approximate equilibrium with each other if the residence time is very long and if Q and C represent the concentrations at the same point in space. You can't, as many students have done on exams, take the concentrations in the liquid at one point in the equipment and assume that to be in equilibrium with the concentration on the adsorbent at some totally different point in the equipment. If we imagine a cocurrent flow, where the adsorbent and the liquid flows in the same direction through the system, we cannot have equilibrium in the inflow, since the liquid and adsorbent haven't been in contact with each other yet. If the residence time is large enough, however, we may approach close enough to equilibrium between the concentration in the liquid and the concentration on the adsorbent in the outlet. This is similar to the temperatures we can achieve in an infinitely long cocurrent heat exchanger, assuming no heat losses. In a cocurrent heat exchanger, the temperature of the hot medium and the temperature of the cold medium approaches the same temperature. Note that in cocurrent flow, the outgoing liquid cannot be in equilibrium with the incoming adsorbent, or vice versa, since the concentrations exist in different points in space. If we imagine a countercurrent flow, where the adsorbent and the liquid flow in different directions through the system, the inflow of the liquid can be found at the same point in space as the outflow of the adsorbent. It is thus the concentration in the inflowing liquid that may be in equilibrium with the outflowing adsorbent. Similarly, it is the concentration in the outflowing liquid that may be in equilibrium with the concentration in the inflowing adsorbent. The theoretically best we can achieve is thus almost equilibrium at both ends. Please note that the concentration Q out on the adsorbent flowing out from the system cannot be in equilibrium with the liquid concentration C out flowing out from the system, since these concentrations exist in different points in space. This is similar to the temperatures we can achieve in an infinitely long countercurrent heat exchanger. In a countercurrent heat exchanger, the hot and the cold mediums flow in opposite directions. If we start with constant temperature on hot temperature side and constant cold temperatures on the other side, the temperature along the heat exchanger will gradually change. The coldest the warm medium can become is given by the temperature of the cold medium flowing in. The warmest the cold medium can become is given by the temperature of the hot medium flowing in. However, to reach those temperatures is impossible, since that would require the driving force along the entire equipment to become infinitesimally small. We thus need both an infinitely long heat exchanger, and we need to wait for an infinite time for the system to reach this point. Still, it may be worthwhile to carry out calculations under these assumptions to have something to compare with. We know for sure that the real system will not be able to become any better than this. Note that in countercurrent flow, the incoming liquid cannot be in equilibrium with the incoming adsorbent, since their concentrations exist in different points in space. For the same reason, the liquid flowing out cannot be in equilibrium with the adsorbent flowing out. They also exist in different points in space. As a final comment on heterogeneous systems, you might wonder how you get a solid adsorbent to flow through a system. Well, typically you don't. Instead, you use what is called a simulated moving bed, where the adsorbent is divided up into several smaller columns. From a mathematical point of view, you then get the same kind of system as if the solid adsorbent was actually flowing through the system, as long as you use a high enough number of smaller columns. Understanding how to set up a simulated moving bed is not required in our basic courses.